In this problem, we're asked to design a reinforced concrete beam that can support an 8-meter span of a simply supported load that is uniformly distributed over the length of the beam. The load is comprised of dead load, which includes the self-weight of the beam plus a superimposed dead load of 40 kilonewtons per meter and a live load of 70 kilonewtons per meter. We note that if we don't know the self-weight of the beam already, it presents us with a slight challenge in that we have to assume a beam weight to determine the self-weight and then design around that assumption. So we'll have to do a few checks and balances to make sure that we assume a correct value and that we incorporate the refinement of that value as we refine our design. As we look at this, we're going to have a few things that are specified in the problem. First off, we'll be using 10M stirrups or transverse reinforcement. Now these stirrups would be a primary function to help hold the steel reinforcement cage together, but mostly to resist shear in the beam. And this example doesn't include the shear design, so we're not going to do not design for shear, nor for the development of the flexural reinforcement. So the placing of the bars and ensuring that the bond between concrete and reinforcement is appropriate. That is a different example for a later day. If we look at the beam itself, then we would have an 8-meter span. There would be a distributed load on this beam, WF. And the magnitude of this load would give us a moment that would be positive, with a maximum moment would be equal to WF L squared over 8. If we look at the factored load, this could be computed as 1.25 times W dead plus 1.5 times W live. The magnitude of the load itself in terms of W dead is still yet to be determined. And the equation for 1.25 W dead plus 1.5 W live comes from our building code of Canada. We note that we don't need to incorporate other load combinations, and there's no pattern live loading needed because we have a simple single span, so this is the obvious case for the worst case load on the structure. Let's look at how we get the self-weight of the beam itself. So to do this, we have to try a section size. We have to basically guess. Now, the magnitude of our guess comes with some experience. I'm going to guess a beam of size 800 millimeters by width 500. Now this is a design, and we're going to see that there's a lot of different decisions we have to make throughout the process. The first decision that sets us in motion is picking a size. Often the size will be constricted. We might have other similar sizes on the floor, and we want to have a level of proportion so that every beam has the same depth and maybe the same width, and we just modify our steel size. Or maybe there's a clearance issue where we need to provide enough headroom in the floor. So we may have constraints upon our beam that make us pick a certain size, or we might have free range to pick what we need. We'll note that if I have an 800 by 500 millimeter beam, I can place a lot or a little steel in there, and that can drastically change the moment resistance of this beam. There's no one right answer. There are more right answers than wrong answers. I mean, we can do better in design. We can always get a better design. But there is no one universal solution, and so we have to start somewhere and go out on a limb and choose a value. The limb we're taking here is an 800 millimeter deep beam. We will mess with the dimensions here to make this work as we move out through this problem. But for now, we're going to choose this, and we'll estimate this section will give us an idea of the self-weight. So in terms of the self-weight, we can say that the density of concrete is 2,400 kilograms per meter cubed. It's an 8-meter long beam with the dimensions of 0.8 by 0.5 meters. So if we look at the W dead for the self, this would be simply equal to 0.8 meters times 0.5 meters multiplied by gravity 9.81 meters per second squared multiplied by concrete density 2,400 kilograms per meter cubed. And this would be a value in W dead self of 9,4 0.00 newtons per meter. And we're going to multiply by 1 kilonewton divided by 1,000 newtons as a unit conversion, giving us 9.4 kilonewtons per meter. Now, as we progress through the problem, there's a good chance that we're going to have to modify this to give us a more accurate value as we mess with the dimensions of this beam. But this is enough for us to now calculate our factored load, WF, is 1.25 times W dead, or 40, plus 9.4. Adding to that 1.5 times the live load of 70 gives us our factored load of 166.8 kilonewtons per meter. I'm just going to put a little star beside that. The star means, to me, we will update this as we refine our section size. Now, if we go back to the problem statement, we'll see that there is no information about the materials that we're putting in this beam. We don't know the concrete strength, nor do we know the steel strength. And so in this case, we're going to have to specify them. And the job of the designer is often to specify the materials. However, the specification of the materials does not come without guidance. For example, in terms of our materials, since this is new construction, we can specify Fy for our steel is 400 MPa. This is our default value. This is what 99% of our steel will be. The exceptions come from us looking at old structures that might have 300 MPa steel or 350 MPa steel or some other value, or more modern or exotic building materials like alloy steels, some types of stainless steels, or fiber reinforced polymers that might have higher strengths. However, rebar, as we know it, is 400 MPa for the standard stuff we can get from most building suppliers, building material suppliers. The value of F prime C is widely variable. Now, we have a lot of reasons why we would choose different values, and this depends on what can be provided to us easily by local manufacturers. If we want to go for a higher strength concrete for whatever reason, we might not be able to get that locally or get that reliably locally. If we want to go for a highly workable concrete mix, we're probably not going to be too high of a strength. And as we get to higher strengths, the cost generally goes up as well. So there's a whole bunch of variables beyond just the mechanics of the structure that go into the value of F prime C. Our typical range for F prime C would be between about 30 and maybe 50 or so MPa for buildings. It could be above that, but it generally wouldn't be below that. If you build one floor out of concrete that's 40 MPa, you should build the whole building out of that same concrete strength as well. That way there's no chance of something going wrong, and there's no issue of you having to keep track of when your different casts are, and making sure that your structure is has enough quality assurance to it. So for this problem, I'm going to specify concrete is 40 MPa. And I've chosen that as the designer. This is my choice, and I can choose a bigger or smaller value if I had reason to do so. So we're just going to assume this for this design. But as I said, generally, the concrete strength is made as a decision at the sort of executive level of the structure before we get into any of these design calculations. And if we run into an issue where we need something higher strength than what we've decided from the beginning, then we can modify that executive decision as we go. So given that information, now I'm going to take the chance to refine my section a little bit. As we know, we just guessed at a section size, and this is what design is. It's educating, guessing to get us started, and then working through an iterative process to refine that into something that's usable. So we're going to refine our section somewhat, and we have some tools to do this. I'm going to go to table 2.1 from the Concrete Handbook to give myself the ability to refine this a little bit. Now, I've taken some photos of this table, and this is what we have here. Oh, pardon me here. That's information we'll use in a little bit. What we have in this table are mechanisms to calculate the moment resistance based on the amount of steel that we've placed into a given section, Rho. And if we explore how this moment resistance is calculated, Kr times Bd squared, where B is the base of the structure and D is the depth to the steel itself, we can see that for our equivalent rectangular stress block that we use according to CSA A23.3 standards, we can do a little bit of manipulation and develop an equation for Kr, a factor that incorporates our reinforcement level and our material strengths. And that will then give us a mechanism to then multiply that Kr by Bd squared. If we look at what goes into Kr, though, we have Rho, Fy, and F prime C are the only variables where Rho is As over Bd squared. For 400 MPa or steel, which is our standard, almost always typical value, we can then play around with the value of F prime C and the value of Rho and develop a table of Kr values. And this is what we have. For 40 MPa concrete that we've selected in this problem, for 40 MPa concrete, we can work our way down. And we can pick out alpha 1 and beta 1 values. That's over here. These values we'll need a little bit later. We'll take them for calculations we do later on. We can pick out the value of Rho Balanced as well. Rho Balanced is a very particular value. It's the value of reinforcement that would cause the neutral axis, depth C, to be such that the strain in the steel is equal to the strain at yield. And this would be our balanced condition. So it's balanced when the steel yields at the same time as concrete crushes at 0.0035 strain. If we have more steel than what would come from this calculation of Rho is equal to As over Bd, and that in percent would be 3.34. If there's more steel than that, value of strain down here is less than the yield strain, and it becomes an over-reinforced beam, and that is not allowed in design. So that's an important quantity. That's as far as we can push this beam. Now, if we look below this section here, down below, we can see all the information that we need to find those Kr values. All the values that we have in the main section of the table are values of Rho, area of steel divided by Bd. What we're going to do is find the value of Rho that we have in our beam. For example, if we had 0.21% steel in our beam, we can then find 0.21 for 40 MPa concrete and work our way across and find the Kr value of 0.7. We then take that 0.7 and put it in our Bd squared times 0.7 equation, and we get the value of moment resistance with a unit conversion factor afterwards. I am going to use this table to help us with our preliminary design here. So since we have moment resistance is equal to Kr times Bd squared times 10 to the minus 6, and this will give us kilonewton meters. Minus 6 is the unit conversion. And Rho is equal to the area of steel over Bd. We can choose a starting point of Rho for our beam that we want. So we will choose a value of rho for our beam. And we can modify this as we go, but this will be our starting point. And this is another designer's decision. I could choose any value between 0 wouldn't do anything, but up to Rho Balanced, not above that. So what should I choose? Well, there's a big question there. If we chose Rho Balanced is equal to the maximum value, and this would be hard to place, hard to fit in a beam. It also has some other drawbacks in that if we have to modify our design just a little bit to make things work, we don't have any room to put any more steel in there. And so we are already at the limit, and that's no good to us. Instead, we will typically, as I guess a rule of thumb or a starting point, unless we have different information, try rho is approximately equal to 0.5 to 0.7 of Rho Balanced. And this is an approximate value. This just gives us a starting point where we have plenty of wiggle room to modify our design. So for this problem, we will use rho is equal to 2.1% as an arbitrary value that is approximately in that range of 50 to 75% or 70% of Rho Balanced. And here, Rho Balanced for this problem for 40 MPa concrete is 3.34%. So if we want a percentage about 50 to 70 or 75% of that, we'll take 2.1. And that 2.1 in this table, let's go back to this table here. So we're going to move down the 40 MPa column and look for 2.1. That's 0.21, so that's not enough. As we keep going, we're going to see if they start to cut off here. And these cutoff values where there's nothing listed, well, those are the values when rho exceeds Rho Balanced. So we're now in the over-reinforced range down here, and we can't design there. So recall we're in 40 MPa concrete, and I said 2.1. Here we go. It's right in that table. We go over and we pick up a value of Kr is equal to 5.9. So for rho is 2.1, Kr is equal to 5.9. And this will give us a beam that has a depth of H, or sorry, a height of H. Here's where our steel is going to be, AS. Here's our D value, and here's B. So if we have that, for H is equal to 800, we can say that D might be approximately equal to 725 millimeters or so. And so the distance below here is needed for concrete cover, for the stirrups, for the possibility that we've got 2 rows of steel and we need to take D to the middle of those 2 rows. So we need to add a little bit down below that. So if D is 725, and once again, we will refine this later. Now we can use our Kr equation. So first off, let's find MF, our factored moment, is WFL squared over 8. And we already have a WF value, 166.8 kilonewton meters times, or kilonewton per meter times 8 squared over 8, giving us MF, our factored moment, of 1,334 kilonewton meters. Since MF is equal to MR at our ultimate limit state, meaning where we design to, we are breaking the concrete beam, so factored moment is equal to factored moment resistance. We have MF is equal to MR is equal to KR BD squared times 10 to the minus 6. Plugging in some values for that, 1334 kilonewton meters is equal to Kr of 5.9 BD squared times 10 to the minus 6 as a unit conversion. And this gives us BD squared is equal to 200 times 10 to the 6th millimeters cubed. For rho is equal to 2.1% and F prime C is equal to 40 MPa, and for our section such that moment is equal to 1334 kilonewton meters. So all of those can change as we need them to, or as the design mandates as we refine our section size. Now, since we calculated for D is assumed to be equal to 725 millimeters, let's see what we get for B. B is going to be equal to 226 times 10 to the 6 millimeters cubed divided by 725 millimeters squared gives us a value of B is equal to 429.96 millimeters. And we will round this to B is equal to 450 millimeters. Now, as you get into design for reinforced concrete, we're never going to design to a strange dimension. Oftentimes we'll have a lot of limitations around the size of the beams that we can make depending on what company is manufacturing them for us, so who's building it for us. They might have pre-formed formwork or pre-made formwork that they want to use, and this might constrain our sizes as well. We don't want to specify something like 430 millimeters because it's an awkward size to build to. It's an awkward size to measure against and subtract from different measurements for people building it. So we're going to round that to a nice even increment of maybe something multiplied by 25 or 50 millimeters. And oftentimes, because of the close proximity to our neighbors down south, we'll have to modify this to some multiple of inches as well. We're going to choose this as our trial size, 450 millimeters. And now if we take our beam here, we're going to have B is 450 and H is 800. So now if we update our loads, our dead load, and our corresponding live load, we can say that our dead load for self weight is now going to be slightly different than it was before. 0.45 times 0.8 times 9.81 meters per second squared times 2400 kilograms per cubic meter times 10 to the minus 3 as a unit conversion to get us to kilonewton meters rather than newton meters. And this would be 8.5 kilonewtons per meter, meaning W dead total is going to be 8.5 plus 40, and this gives us W dead of 48.5 kilonewtons per meter. And if we look at what we had in the previous calculation, we had 49.6. So we see it's certainly not very sensitive to a change in geometry because of that large value of superimposed dead load, but we should still update the value of WF and MF before we move on. WF is now going to be equal to 1.25 times W dead, 48.5, plus 1.5 times WL, 70. And that's going to be equal to a value of 165.6 kilonewtons per meter. And our factored moment MF is WF L squared over 8. And this is 165.6 times 8 meters squared divided by 8. Our factored moment for that section size is now 1325 kilonewton meters. And this is our updated value that we're going to design to until we change our section size if we do so again. So this is for B is equal to 450 and H is equal to 800 with an assumed concrete density of 2,400 kilograms per cubic meter. Now we're going to take that information and now we're going to have to attempt to figure out how we're going to place our steel to withstand that amount of load. So here we're going to find our bar size and distribution. And to do that, we're going to have to look at things like cover requirements and spacing requirements. Let's build ourselves a little sketch of a beam here and see what we can make of that. If we've got our beam, and this beam has inside of it stirrups. These are our transverse reinforcement, and these are specified at 10 M bars, so these are 10 M stirrups, which would have a bar diameter of 11.3 millimeters that we can look up in the table in the concrete handbook. On top of those stirrups, we're going to place longitudinal reinforcement, and there's a possibility that they could be in 1 or 2 rows. What we need to provide for in this beam is cover, and we need to ensure that we have the appropriate levels of spacing, and additionally spacing here. We can specify those values, and to do that we have to ensure that we meet the minimums. So if we look at cover, we can say that BC prime minimum is equal to the maximum of 30 millimeters, 1.0 times our bar diameter, and 1.0 times the maximum aggregate size in our concrete mix. And BC prime is our clear cover to the bottom of our, or to the outside of our stirrups, where BC would be the cover to our longitudinal bars. Additionally, we're going to have spacing requirements, where the value of S minimum is going to be the maximum of 1.4 times our bar diameter, 1.4 times the maximum concrete aggregate size, and 30 millimeters. So here we're going to specify A max is equal to 19 millimeters. And this is a somewhat default value as well. There are a bunch of reasons why we would use bigger or smaller maximum aggregates in the concrete, but that's not for this particular topic here. But they can have to do with the size of the forms that we're working with, or the size of the cross sections, what we need to flow into what materials. And as we get, or into what zones, and as we get higher strength concrete, the aggregates start to become the weak part of our concrete mix. Now, this is usually for very high strength concretes, but in that case we're going to remove a lot of our large aggregates and use smaller size fine aggregates instead. So there's a whole host of reasons why we'd have different A values, but typically for most concretes in the range of 30 to 55 or so MPa, our largest concrete aggregate size is 19 millimeters, which is 3/4 of an inch. Now, let's look at something else here. Since we have Rho is approximately equal to 2.1%, and this is equal to area of steel divided by B times D times 100%. We can say that area of steel is approximately equal to 0.21 or 0.021, for that in decimal instead of percent, times the cross-section size of 450 millimeters times the value of D that we've assumed of 725 millimeters. And so here in these values, this is B and this is D, which is assumed. We don't know that for sure yet. So this means that we're looking to put in about 6,851 square millimeters of steel. This is what we think we need in there. But we're going to have to check that as we get the actual value of D. Additionally, we need to take a look at how we can place that. So let me draw a little bit of a blow up of what we might have in there. Let's use straight lines. Let's draw a blow up of the cross section itself. So if this is our concrete section and we're cutting it off there. Inside of it, of course, we're going to have our stirrups. Those should there. And they've got a dimension to them as themselves. And then inside of that, we're going to have whatever longitudinal rebar we have. So looking at all this, we need to measure some stuff out. First off, we can say that the outside dimension of this thing is going to be B, the width of our beam. Then we've got some stuff happening inside. We've got the distance between the edge of the beam and the outside of our 10M stirrup is BC prime as the minimum value that we're going to put there. So we have to at least put that there. And of course we have the same on the other side. Additionally, we've got our diameter of the bar for a 10M, and that's 11.3 millimeters. And we've got a bunch of our bar diameters themselves, dB. We don't know what bar size we're using yet. And then we've got some spaces between the bars, and so this would be S min. Now, if we look at this, we can say we've got a number of bars we can set equal to n. In this case, I've drawn n is equal to 3. If I have n bars between the bars, I have n minus 1 spaces. So I've got two covers, 1, 2, two stirrup bar diameters, n bar diameters, and n minus 1 spaces. Adding it all up together, I can say that B, the width of the concrete section, has to be greater or equal to the sum of all the components that are going inside of it. N times our bar diameters plus 2 times BC prime minimum plus n minus 1 times the value of S minimum plus 2 times 11.3, which is our stirrups. So if I take that equation along with the equations that I have up above, let's just use this in red here to show what I'm looking for, or color I haven't used on this page, purple here. If we take this equation for B, these equations for the value of S minimum and the value of BC prime, along with the equation for area of steel that we need, 6,851, we can start to try and play around with the number of bars and the bar sizes to make that fit. And that's what I have in the table on the next page. So let's go to that table and take a look here. A small table, and in this table, we're looking for an area of steel has to be greater or equal to 6,851 millimeters squared, where area of steel is equal to N times area of the bar. So if that's what we have, let's fill in this table with some information. we have our bar size or a designation, and we can go, let's start with 20M, 25M, 30, and 35M. We don't want to go bigger than 35. They become hard to put in on the job site, hard to move around, and you really don't make any friends with the people installing those bars when they get so heavy. And we'll see that if we start to go small in these bars, 20M and lower, they become so small area that we need way too many of them to work with for this size of a beam. So we're going to explore what these bars sizes are and how they relate to this, but we'll see soon that there's some obvious choices we can make. We can pick out the bar diameters and working our way across here, 19.5, 25.2. All of this is coming from the handbook. These are Canadian manufactured bars and they're of a standard size. These are the nominal equivalent cross-section diameters. Really, they're manufactured to hit a certain bar area. A 20M is a 300 square millimeters, and we have 500 at 25M. 700 for a 30M, and 1,000 square millimeters per bar for a 35M. If we then take our equation up above, area of steel is equal to N times area of the bars, and set area of steel equal to 6,851. Solve for the nearest integer, N, that is greater or equal to, that gives us an area of steel greater or equal to AS. We can find that with 23 bars for N here, and 14 bars for 25Ms, 10 bars, and 7 bars all the way down to 35Ms. This gives us areas of steel of 6,900 at 20M, 7,000 for all the rest. So those are the minimum amounts of steel that we need to achieve, or of bars we need to achieve that 6,851 square millimeters. Going to that cover equation, we can calculate BC prime of 30, 30, 30, and by the time we're down here, it's governed by bar diameter, not that 30 millimeter default value, 35.7. Then we can find S minimum, the minimum spacing of bars, 30, 35, 42, and 49. If we then go to the equation we developed above, we see here that we have B has to be greater than all this stuff. Now we know S min, we know BC prime, we know DB, and of course we know, 2 times 11.3 millimeters here for the stirrups. We can solve for the value of N, number of bars, that can fit within B without exceeding that amount. And in doing so for each of these, we can come up with the number of bars in a row, bars per row, and we have 8 bars fit across that section for a 20M, 6, 6, 4 as we approach 35M. This means that if we have 23 bars for the 20M and 8 bars per row, we're going to need to have, in terms of number of rows, 23 divided by 8 gives us needing 3 rows, maybe not all of them full, but 2 full and 1/2 row basically. 3 rows, 2 rows, and 2 rows. This is enough information for us to make some educated choices around the bar sizes that we're going to use for this design. If we take ourselves this 20M bar, we're going to need 3 rows to fit them all in there. And this will be an awful lot of steel to tie in place. It'll cost a lot of money to tie it. And the location of these bars, so this would be a sketch of, I'm not going to draw them all here. Well, this would be for the 20Ms. I might end up putting, I can fit 8 across, so I'd fit 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. And then I'd have to do above that, I'd get all the way up to 16. And then I wouldn't want to put 7 above that. That's an odd number. I'd have to put 8 above that as well to make it a nice even number. And by the time I do that, my value of D is small because I have a lot of bars in there and they're moving up towards the neutral axis, which will mean I'll have to increase H. So that doesn't really work out. Conversely, if I go to 35 M bars, I'm going to have 4 bars, 2, 3, 4, and I need 7, so I'm going to put 1, 2, 3, 4 to even it out again. And these bars will have, so I'm going to have to put a bunch of extra stuff in here, but I'm going to find that this will give me problems with crack control problem. May not, but it may be a problem. Now, additionally, in this case, the value of S is 49 millimeters and the value of the bar diameter is 35.7, meaning that my value of D is going to creep up fairly high just for 2. Right in the middle, in the Goldilocks zone here, I can see that I've got 30 M bars where I can place across them 6 bars per row. Well, actually, I'm going to draw this below instead because I'm going to explore 2 choices. So, likely, the best choice will be the 30 M bars because of what we've been discussing. It sort of has the best mix between the two. There's the, we can almost fit all 10 of them. Well, we can fit all 10 comfortably in 2 rows, and it limits the value of D as small as big as possible, and it has enough bars to help us with crack control. So let's explore what we can do with this. So if we've got now 10 30 M bars, we have 2 choices. We can draw a cross section with 1, 2, 3, 4, 5, 6 bars there. And then on top of that, 1, 2, 3, 4 bars here. Or we could draw a cross section that, well, it's going to look a little nicer than that. It's going to have 1, 2, 3, 4, 5 bars and 1, 2, 3, 4, 5 bars. Either are acceptable. If we look at this option over here, we could say this will have a slightly larger value of D than the value over here, all else being equal. That's because the neutral axis, or sorry, the centroid of these bars is a little bit closer to the bottom than the centroid of these bars right in the middle. But that's going to be very negligible. Either are fine. We'll note that as we place them, we're placing all the bars right on top of the other bars. And this allows for the concrete to flow around them without any issues. And so as they're tied together into a cage, that would be the standard practice. What we're going to do for no particular reason, other than it's slightly simpler to calculate and slightly simpler to tie, is we're going to try this arrangement. But both are acceptable. In fact, the arrangement we're trying will end up being the slightly weaker of the two because of the D value will be slightly lower. But it will also be slightly easier to build and very, very slightly easier to compute. So let's find D. So let's redraw this out a little bit bigger. We've got our section here. We've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 10 bars. And D will be the distance right to the middle of those 10 bars, right in the middle here. Between them, we're going to have the value of spacing that we're going to provide. And then we're going to have underneath that, we're going to have the bar diameter dB. And then beneath that here, we're going to have this value will be BC prime plus 11.3 millimeters. And that will be the stirrup. And of course, the whole thing, so this is D here, the whole thing will have a height of H. So this isn't too hard for us to compute. The value of this, by the way, we're going to need this later on, this dimension here later on. So this dimension here would be Y is going to be equal to H minus D. We'll need that for some crack control stuff later on. If we do our Y calculation, this would be BC prime plus 11.3. That brings us to the bottom of our first row of bars, plus DB plus S over 2. Now, if we happen to have chosen this one, we would do a similar calculation, but of course we'd need to find a different distance than S over 2 to the center of those bars, so we'd have to use the moments of their areas to find that. We noted above that S min is equal to 42 millimeters. Now, as a designer, we would be doing a disservice to the people building these things if we specified 42 millimeters. So we will use S is equal to 45 millimeters. Now that's the dimension in the vertical direction here. What they're going to end up doing as they place it across there, they'll place these stirrups at the locations of the cover, and then they're just going to distribute the 5 bars across with very, by eye basically. They might not even measure that. And by our calculation in this table up above, we know that we can fit 6 bars across there. So we're comfortably within the minimum S range across there. But this dimension here, we do have to specify or they won't be able to place that. Now, another thing to note is that when these bars are placed, they're often placed by putting either a plastic or a ceramic or masonry type rebar chair down that connects to the bottom of the form or sits on the bottom form, and then all the bars sit on top of that. And so depending on the size of the chair, we might have to change that value of S to 50 millimeters or something, depending on what we can get. But that is really something that we can't incorporate in this level of design that we're doing today. Instead, we'll use 45 millimeters as shown here. And from that, we can then calculate Y is equal to 30 plus 11.3 plus 29.9 plus 45 over 2 gives us Y is equal to 93.7 millimeters. This gives us D, because we've used H as 800. D is equal to 800 minus Y, 93.7, is equal to D of 706.3 millimeters. Now let's note that this here is different than D is equal to 725 that we have assumed to date. But if we look back at where we used that, well, we just used that to specify, well, let's look back really quickly where we mostly used that. We picked a value of D here to use, And that D gave us the amount of steel that we're going to need in the equation up here. Where is it? Here. KRBD squared. So we picked a value of D. When multiplied by KR and B and squared, it gave us our moment resistance to give us a 1,334. And then what we did was go ahead and find something that reduced that moment a little bit, so we don't need quite as large D. That's not a considerable thing though. But from that calculation, we saw that we needed, when we did this rho calculation here, we needed 725 times 450 times our assumed 2.1%, 6,851 square millimeters at 725 millimeters depth. But what we end up putting in there is 10 bars, giving us 7,000 square millimeters, which is more than 6,851. So we have a smaller value of D, but a larger value of AS. So it might work. And we're going to hope it does, and if it doesn't, we're going to have to adjust our design a little bit. We aren't going to go backwards and fix anything yet, though. So let's see how we did. Find MR and check that MR is greater or equal to MF. And to do this, we could either go to table 2.1 again, or we can use a more first principles approach. So I'm going to use the other approach here, the equivalent stress block approach, just to give an overview of exactly how that's done. We've got a stress block here. I'm just going to move that down a little bit to give myself a bit more working room here. We've got a stress block. It has a height here of A is equal to beta 1 times C, our neutral axis depth. It has a compression block depth here, or magnitude of alpha 1, phi C, F prime C. There's a compression force, CC, located at a distance of A over 2 away from the top of our compression block. This is our neutral axis here, by the way. So this would be our depth C. And down at the bottom here, we've got a tension force in steel is going to be equal to phi S, area of steel, times Fy. The distance between the two here to here is D minus A over 2. So using that compression block, we should be pretty good to go to compute the internal moment resistance. Now let's look at that. First off, we know that alpha 1 is 0.79 and beta 1 is 0.87, and we chose those from table 2.1, or we could always compute them out using their equations. But we saw them earlier on, and this is for F prime C is equal to 40 MPa. Concrete. Now, one thing I didn't mention about table 2.1, let's just go back to that just for a quick second. Imagine that we had 42.5 MPa concrete somewhere between. Well, if we had 1.8% steel, we could go and pick off the value for 45 and the value for 40 and interpolate the value of Kr between the two. We can also interpolate if we had 40 MPa concrete and we calculated rho S is equal to 1.82 somewhere in here. We could pick off the value of 1.8 and 1.84 and interpolate between those two appropriately. So if you're using table 2.1, we have to be able to interpolate across values if we don't have something exactly in the table. The next thing we need to do is find the value of our tension force in the steel, and we know by definition steel has to yield or the beam is over reinforced. This beam will not be over reinforced since we have chosen rho to be under Rho Balanced, but we're going to check it again later anyway. And we have an equation phi S, area of steel Fy. That's 0.85 is phi S times the area of steel 7,000 square millimeters multiplied by 400 MPa. And this will give us a value of TS in newtons is 2,380 times 10 to the 3 newtons, or 2,380 kilonewtons. Then we can say that the sum of forces has to be equal to 0, so therefore our concrete and compression has to be balanced by our tension steel. If we do this work, we can say that, let's write it in terms of A times alpha 1 times phi C times F prime C times the width of the section has to be balanced by phi S, area of steel, Fy. So therefore we can solve for A is equal to phi S, area of steel, Fy, divided by phi C, alpha 1, F prime C, B. Plugging in all these values, we get 2,380 times 10 to the 3, divided by 0.65 is phi concrete, 0.79 is alpha 1, 40 MPa concrete strength, and 450 millimeters is B. Gives us A is equal to 257.5 millimeters across, or down to the bottom of our equivalent concrete stress block. And C is going to be equal to A divided by, oh, it's messing up on me here, A divided by beta 1. And this is going to be 257.5 divided by 0.87. C is 296 millimeters. Now we know for a fact that this is under reinforced, but we still want to check that the value of C to D, that's D and this is C, this is epsilon steel, and this here is epsilon of concrete. So when this is equal to 0.0035, we want to make sure that epsilon steel is greater or equal to epsilon Y. And to check that, we take the ratio of C over D and set it less than or equal to 700 divided by 700 plus Fy. And that's all through similar triangles and converting strains into stresses. And so 296 divided by 706.3 has to be, which is equal to 0.42, has to be less than or equal to 700 by 700 plus 400, which is equal to 0.64. So we are okay, this is under reinforced. Which is good. If it wasn't under reinforced, we stop, we rethink, we redesign, because there's no fixing that without adding compression steel that we'll talk about later, or without changing our section size or reducing the steel in the section. But it's not acceptable to have over-reinforced in our design. MR, our big one here, our moment resistance, then becomes, so let's take a look at what this is. The internal moment here is going to be the moment of our couple. We've got compression and tension here, and we've already said they're equal to each other. So the moment of our couple is the magnitude of force multiplied the moment arm between the two. And the magnitude of force is TS or CC. We already know TS, so we'll use this, times D minus A over 2. Putting in the values for this, we have 2,380 kilonewtons. That's our tension force, multiplied by D minus A over 2 is 706.3 minus 257.5 by 2. Times 10 to the minus 3 meters per millimeter. Gives us a value of MR is equal to 1374.6 kilonewton meters. And of course, limit states makes us ensure that MR has to be greater or equal to MF. 1374.6 kilonewton meters is indeed greater than 1325 kilonewton meters. Therefore, we are good for moment resistance. And we've got a beam that so far is able to withstand everything we need that we throw at it. Now, if it wasn't, well, first off, let's just take a quick look at this. Look at how good we did. We got it within, a few percent of where it needed to be. That's excellent work. The reason for that is we didn't just take a stab in the dark and just throw some random steel in there. We used the tools we had available to us in table 2.1, and we chose an estimate of size and then picked an amount of steel based on reinforcement ratio, and then worked off of that to try and design around it with a rational process that got us there, in fact, in one step. Oftentimes we won't quite get there in one step, though. We might get a value that's slightly under. If we don't get lucky, or if we weren't careful enough in this process, we might have ended up with 1200, and that's not greater than 1325, so we need to redesign. What do we do in that case? Well, here we need to think about that, and so here, so we can write if MR is not greater than MF, then we have to do some redesigning. In this case, then we're going to redesign. And to do that, we can do a few things. We can increase H, the section depth, the section height, and therefore increase D. We can increase B, and in doing so we would have more concrete in compression, and so that would allow us to have a neutral axis that would be slightly we would change the value of C in that case, and that would give us a slight benefit, but not very much necessarily. So let me just go back briefly to what that would do here. Increasing B would make this value here go a little bit higher, which would move A over 2 a little bit higher, so D minus A over 2 changes a bit. And then we could, if we wanted, we can increase Rho is equal to AS over BD, so more bars here. And we note that we had the possibility to put actually 6 bars per row, so we could go up to 12 bars quite easily. Be careful about not exceeding row max, though. And of course, if we are able to, if there's nothing stopping us, we can increase F prime C. So what we would typically do, though, is we would do one of these two. So we would mess with those. These are the most common options. Normally we wouldn't really have much leeway on F prime C, and we note that increasing D is far more effective than increasing B. Now we need to also ensure a couple things. Hopefully this stuff, though, is just a check, not requiring us to do a redesign. We're going to make sure that we pass our crack control requirements in table 2.7 and our skin reinforcement requirements in table 2.8. So for crack control requirements, we're going to compute Z is equal to FSDC A to the 1/3 power and compare it against what we have down here for Z maximum values. Now, in this case, if the problem didn't specify this, let's assume if it was not given, I guess it must have been given, so we can do our cover here, that this is interior. So this means that Z has to be less than or equal to 30,000 newtons per meter, not exposed condition. So let's go through some of these calculations. If we look at our configuration, we've got a configuration that has 2 layers of steel. They've got 5 bars per row. And we note that we've already computed y, and where y is equal to h minus d. And we have enough information to find dc. So let's first write what we know here. We know that y is equal to 93.7 millimeters. And we know that DC is going to be equal to our cover 30 millimeters plus the stirrup diameter 11.3 millimeters plus our bar diameter divided by 2. The depth to the bottom, centroid of the bottom layer of reinforcement. DC is 56.25 millimeters. And now if we compute the value of A is going to be equal to the shaded area 2y times B divided by 10 bars. So that's 2 times 93.7 times 450 over 10. A is equal to 8,433. And this finally, Z is equal to, before we do Z, let me get Fs, maybe taken as 0.6 Fy, 0.6 Fy, which is 240 MPa for 400 MPa steel. So Z now computes out to be 240 MPa multiplied by DC 56.25 times A of 8,433 to the third power. So Z is equal to 18,716.6, which is less than 30,000 requirement. So therefore, we are okay. Now, there's always the possibility that we're not okay. So we'd say, if we don't pass this, now we have to use more bars. So we would, instead of using 1035 or 30 bars, 30 M bars, we would use the equivalent amount of 25 M bars to increase the number on the denominator of A, which would give me a smaller value of Z. And this is what I was worried about with those 35 M bars, that if down here, instead of having 10, we threw in 6 bars or whatever it was, we would have possibly had an issue with passing this. Since we passed that, we need to look for a skin reinforcement and see if we need any of that. Skin reinforcement's only necessary where the height is significant. So here, if H is greater than 750, we might need to have this, or we would need to have this. Once again, we have interior exposure. So when H is greater than 750, what we're going to do is calculate the areas of these strips, and then take the areas of the strips and multiply them by 0.008. Take the total area, divide by 2, or take each strip on each side and just multiply by 0.008, and that'll be the area of steel we placed there. Let's do some of these calculations then. We know that H is equal to 800, is greater than 750, so therefore we need the skin reinforcement. Shifted up on me. So since we need this, we're going to have to find some stuff. We're going to need 2 times H minus D, this value here. And this is 2 times 800 minus 706.3 or 187.4 millimeters. We're going to need h over 2 minus 2 times h minus d. So h over 2 minus 2 h minus d gives us 800 over 2 minus 187.4, or 212.6 millimeters. Now, I'm missing a little sign here. There needs to be a greater or equal to sign there, meaning we have to distribute reinforcement in this region that we've just found that measures between 187.4 millimeters off the bottom up 212.6. So in this region, we have to distribute with no more than 200 millimeter spacing an amount of steel along the height here. So let's take a look at what we need to put in there, and then we'll see what we have to do with it. Now, generally, we don't need much steel there, so what we're going to do is assume 10 M bars, and this is almost always going to be the case. Sometimes 15 M bars, but almost always 10 M bars for skin reinforcement. And then we're going to calculate that value of X. So with 10 M bars, X is going to be equal to B over 4, and this is going to be equal to 450 divided by 4, which is, or sorry, not 450 over 4, that's the limit to it, I'm sorry. X is going to be equal to the distance from the edge to the center of those 10 M bars. X is equal to BC prime plus 11.3 for our stirrup plus 11.3 over 2. So here this would be our stirrup, and this would be the skin reinforcement. And crunching those numbers, we end up with 47 millimeters, which is less than BW over 4, which is the width of the beam, which would be 450 by 4, and whatever that computes out to be, I guess, so 112.5, I think. So this value is equal to X, 47 millimeters. Now, if X was greater than that BW over 4, we just use BW over 4, and what it just means is that the shaded area becomes the full width of the beam. Now we find the area of the shaded area. ACS is going to be equal to 2 times 2x times h over 2 minus 2 times h minus d, which gives us 2 times 2 times 47 times 212.6, or 39968.8 millimeters squared. So this means area of our skin reinforcement per strip simply becomes 0.008 times ACS divided by 2, or 0.008 times 39968.8 by 2 is 159.9 millimeters squared per strip. So therefore, let's use 2 10M bars per strip, which is a total of 200 millimeters squared. And we're also, since we've only got 2 bars and we're trying to fit them in 212.6 millimeters here, and we can't use more than 200, let's just use the maximum spacing to fit them. So here we will use S is equal to S max for this part of 200 millimeters. Let's say that we had 3 bars. Well, what we would do is specify in our details a starting point, an ending point, and a middle point for the bars that added up to some nice dimensions that would be easy for somebody to place in the field and fit within our maximum and minimums. But here, since we just have the 2 bars, it's very simple for us. We'll pick that 200. We don't want to be right at the edge because that's 216 or 212.6 isn't a very nice round number, so we'll pick 200. So all that's left for us now is to give some specifications, some details in a summary, and then we finished our problem. Everything's passed and we have a very efficient design that satisfies all cracking control requirements. So first off, MR is equal to 1374.6 kilonewton meters is greater than MF is equal to 1325 kilonewton meters, and we did update all of our dead loads, so we're good to go. We also specified Fy is 400 MPa, F prime C is 40 MPa, BC prime is equal to 30 millimeters to the 10M bar. We chose an spacing for the vertical bars is equal to 45 millimeters, and we'll actually show that in our drawing, so we don't need to specify it here. Let's give ourselves a little bit of a drawing. Here's our beam. It's got a height here to here of H is equal to 800 millimeters, and it's got a base here to here of B is equal to 450 millimeters. Inside of it, we're going to have a stirrup that was given to us as a 10M bar. So this is 10M. We know that inside of that we've got 1, 2, 3, 4, 5 bars. On top of that, 1, 2, 3, 4, 5. So here we've got 10. Well, let me actually put that in a different spot. Oops. Oh, it's unfortunate. Oh. There we go. All right. Inside of here, we've got 10 30M bars. And we are going to want to provide some dimensions. So inside here to here, this is 45 millimeters. We've got a couple of 10M bars. And those 10M bars are spaced at 200 millimeters. Those are a skin reinforcement. If we place that, we see that a nice place to put that fits within those values that we found and is a nice round number is 190 millimeters. And that's about all the information that we need to provide in order to have this beam be made. So we've given all the necessary dimensions either on the drawing or up here in terms of cover, and summarize our moment resistance. We'll note finally, as was given in our problem, that we still need to ensure that our shear resistance is greater or equal to our factored shear force, and we still need to develop our bars So this would be ensuring that we have proper bond and development length, and we space our bars appropriately along the plan and elevation of our beam rather than just through our cross section. But otherwise, we have finished our problem.